Thank you very much. You know, one of the things I want to say is that math and science is not only very important to the world, it's also a lot of fun. And so hopefully today we're going to look at the more fun aspects of what you can do with these things. And the thing I want to instill in you is the feeling of wonder that science can give us. If you look at the natural world around you, you see all these wonderful phenomena and you want to learn about them, whether it be through math or just observation. Observation is key. I've got 3 different exhibits here today I'm going to be talking about. 2 of them have to do with electricity and 1 of them has to do with sunlight. So without much further ado, I'm going to start with the first one. Now, how many of you have scuffed your feet across the carpet and then come running up to a friend and touched them like this and given them a shock? Can I see a show of hands? What you are doing is being in electrical generators. You are essentially creating static electricity on yourself. And how is that possible? Well, that's possible because electrons are not very tightly bound to the atoms that they are associated with. So if you scuff your feet across the floor, you're literally scuffing electrons off the carpet onto you. And then, since you've got insulated soles that don't let them get off, these electrons are all on you and you're charged up. And if you then go to somebody else who isn't charged up and you touch them or you touch a doorknob, you'll get a shock. Now, does anybody know where the word electricity comes from? Where does that come from? Does anybody know historically? Well, it's from the Greek word elektro for amber. And the reason that is so is that way back in ancient Greece, people found out that if they took an amber rod and rubbed it, it would attract things to it. It would pick up little pieces of paper or whatever it might happen to be. And the same thing happens if you stroke a cat, or something like that. You'll get this charge. Well, in the 17th and 18th century, inventors developed what are called electrostatic generators. I have an example right here called a Van de Graaff generator, and it's really just a big version of scuffing your feet across the carpet. There's the ground bottom here. There's an insulated column, and there's a sphere on the top, and there's a belt that goes around. And that belt carries the electrons up, and they jump off because they don't like each other, and they end up on this sphere here. So if I turn this on, you might want to turn the light down a little bit so you can see this a little bit. I'm getting about 100,000 volts here. See a little bit better here. And what's happening is this is grounded and the electrons don't want to stay up here. The one thing they want to do is get off of this. They're coming to me too. I'm getting shocked right now, right here, okay? If anybody wants to come up and try this out, they can, And the more I pull this away, the faster it goes, and it's jumping all the way almost a foot across here. So there's a lot of voltage here between the differences between them. Well, okay, here are a couple of other things. How can you get them to come off? Remember, they want to leave from here. Well, I can put this up here. What do you suppose is going to happen when I put that up here? Let me see, I'll take this and maybe put that on like that. What do you suppose is going to happen when I turn this on again? It's going to spin. Let's see what happens. See it going? And if I bring this in here, it's still coming off, you see, because this is charged up now. It spins around pretty well. Okay, let me show you another experiment you can do with this. As the electrons stream off the end, they push this around. It's Newton's third law of motion, but with electrons instead. Now, let me make sure there's no charge on here. Now, I'm going to put some little punchies on top of here, little paper punchies. The university is going to love me for this one. What do you think is going to happen when I turn it on? They're going to fly? Sounds like a pretty good? Let's see what happens. It's a great way to make a mess. But you see, I'll show you something else here. Now I said, I think this will work. Now I'm going to come over to this right here. Didn't. No. Now you see it's jumping all the way down to the floor. So, static electricity is charged all in one direction. It's like direct current. There isn't any current flowing until that spark jumps. So that's why we call it static electricity. But nevertheless, it's direct current. This is charged negative, and this is charged positive, essentially. It's just like lightning, essentially, but on a small scale. So that's that. And it was the development of these machines in the 17th and 18th century that led to just people like Benjamin Franklin is probably the most famous one, discovering that one, that lightning is electricity, and two, that there's a potential to use this for other things. And so a lot of experiments were done at that time, so that by the early 19th century, about 1800, you began to get the real development of electricity. And of course, we know how dependent we are upon electricity. Well, I'm going to jump forward about 100 years now to the 1890s. How many of you have heard of Nikola Tesla? Good number of you. Well, Nikola Tesla was a genius electrical engineer who lived between 1856 and 1943, and he was both one of the most brilliant electrical engineers to ever live, and also quite a showman. Tesla, among other things, invented the modern electric motor that's used in industry, the induction motor, but he also became very interested in something called resonance, and he became particularly interested in what are called resonance circuits. Now, you think about what's the big deal about that? Well, I want you to think about something, and that is that you all have cell phones on you, most of you. And how do those cell phones communicate with the other people? How do you do that? How has that wireless communication occurred? Anybody want to say? You got anybody wants to say that? What happens? How does it work? What's the principle? It's called electromagnetic radiation, or radio waves is an old-fashioned term. Essentially what happens is you have a little transmitter in your phone that broadcasts your voice to a tower that then transmits it across to other towers, and that's how you're able to communicate with it. Well, that whole system of radio was first proposed that these electromagnetic radiation waves must exist by James Clerk Maxwell in the 1860s. Scientists hadn't found them yet. But in 1886, Heinrich Hertz in Germany did the first experiments that showed that they did exist. Nikola Tesla got very interested in that, and he began to explore ways to generate these radio waves and to use them commercially. Tesla, in the 1940s, was officially declared the inventor of radio. And so you can thank Nikola Tesla for your cell phones, in a sense, because that's the whole principle on which it works. Well, what are electromagnetic waves? They are essentially just like light, except that they are a much lower frequency. You can't see them. And it's basically reversing back and forth several thousand times a second. And so we refer to that in hertz. And so when you tune in your radio station, and it's named in honor of Heinrich Hertz, when you tune in your radio station at, say, 97.5 or 91.7 University of Michigan radio, that's at 91.7 megahertz, meaning million hertz per second. Okay, well, Tesla began to experiment with how to do this. Now, what Hertz had done is he'd taken a spark gap and he had put a capacitor in series with the spark gap to create a resonant circuit with a coil. I have what's called a Tesla coil here, which was developed by Nikola Tesla in the 1890s. This is a modern version of it, and essentially down below there's a spark gap, which you'll see operate in a minute, and there's a transformer that steps the voltage up to about 4,000 or 5,000 volts, and there's a capacitor. This has thousands of turns of wire on it, and this has only a few. And if the resonance is right, this acts as a thing to step up the voltage to very high levels. And I can turn this on, and it'll make quite a bit of noise. And you can see the spark down there, and you can see what's happening here. Now you'll notice it's also affecting my microphone, okay? And that's the radio waves. What you're seeing, the actual electricity jump here, which is in, again, about 50,000 volts. But there's a big difference between what you see here and what you were just watching with the Van de Graaff generator. Here, it's not static. There's not a charge of, say, negative charge up here, 50,000 volts. This is reversing at about 100,000 times a second, back and forth, back and forth, back and forth, and back and forth. And it's that pulsing up and down like that that creates what's called damped oscillations coming off like this, and they go boom, and then they come down, boom, and then they come down. And that creates a damped wave that creates those electromagnetic waves that radiate out from this. Now I could show this a little bit with this. Wireless light. See this? Now I'm going to talk a little bit more about Nikola Tesla in a way that you probably have not thought about it. This is a picture of Mr. Tesla in about 1900, and he's out in Colorado Springs, Colorado. Can you see this? And this is a trick photograph. He wasn't really sitting in there when he did this. Nevertheless, this is an enormously powerful Tesla coil that can produce millions and millions of volts of electricity at this high frequency. And what Tesla was trying to do was to create wireless light. But he produced this photograph for another reason. He was essentially a showman. And in the early 1890s, he became famous for doing electrical demonstrations, very much like the one I'm doing right now, where he would illuminate himself, he'd have electricity all over him, and he created this showman attitude. At the same time, he was not very good at working with other people. And so, as a result, Tesla's career, which peaked about 1895, began to fade after that because the engineering community didn't want to take him seriously because of all of this showmanship, and he wasn't good at organizing and doing certain types of thinking that are critical in inventing something that's a usable product. There are two types of thinking that are necessary to make a great invention. The first is called divergent thinking. And that means you think of an idea like the Tesla coil, and you think, what are all the wonderful things I can do with this, okay? And you think, oh, I could do this, I could make a radio transmitter, I could make something to help people's health, I could make something to test whether an insulator is good or not, and all these different things. That's called divergent thinking. But there's another part of the inventive process that Tesla was probably the greatest divergent thinker in history of science, I think, in many ways. But there's another aspect of this, it's called convergent thinking. And that's when you take your idea and you do research and you do the development. You take that idea and you make it practical for some practical use. Like, for example, you say, I'm going to make just a radio transmitter out of this, and I'm going to do nothing but work on radio transmitters. Tesla was arguably one of the worst convergent thinkers that we've ever known. He wasn't good at that. So as you students develop careers in science and mathematics, remember this. Remember Nikola Tesla, a great man, made huge contributions to the engineering history and to its understanding of a lot of different things. But he had a lot of trouble later in life because he could not look at both those things, and he didn't understand about how to work in a team with other people in a major sort of way. So as a result, his career kind of faded. So that's kind of an important thing to think about as we go on with that. So that finishes Tesla. Now I'm going to turn to something else, and I'm going to start out by doing something I bet you didn't expect to get at a math competition. I'm going to read you a poem. And this is a poem that was written. Anybody here know who Robert Louis Stevenson was? Can I see a show of hands? Anybody? Good, good. He was a late 19th century writer. He wrote Treasure Island. And he also wrote a book called Child's Garden of Verses in 1885. And I just want to read you one little poem from that, which is about this exhibit in a way. It's called Bed in Summer. In winter, I get up at night and dress by yellow candlelight. In summer, quite the other way, I have to go to bed by day. I have to go to bed and see the birds still hopping on the tree, or hear the grown-up people's feet still going past me in the street. And does it not seem hard to you when all the sky is clear and blue, and I should like so much to play, to have to go to bed by day? Well, that's because he lived in Scotland. And Scotland is even further north than we are here. And I'm sure all of you are aware of the seasons. Do any of you actually watch the changing seasons? Do you actually observe them? Do you spend time looking at the wonder of the world around you to see the magic of how the sun moves through the years? Anybody do that? Does anybody spring hurry? They say, oh, the sun is coming up a little earlier each day, and it's going down later in the day, so I have more daylight. Anybody do that? Any of you? Well, you really should, because it's a wonderful part of life that we live in this world. We live in a world that has, and I got to make sure I get my figures here right, we are at 42.3 degrees latitude north from the equator, and the world is set at an angle of 23.5 degrees, so that in the summer, here, we're in the northern hemisphere, the sun shines on this part of the earth longer, and so you get longer days. And in the winter, over here, it shines less length. And in Ann Arbor, so I decided to build an exhibit that showed this from your perspective if you're on the earth right here in town here. This only works for Ann Arbor or anything else on this particular latitude. Basically, I have a light that represents the sun that's here, and I am now at sunrise. And I've got this set approximately to the time of year that we are right now, which is in early April. If I begin to move this across, you'll notice the sun rises, comes across like so. Here's high solar noon, which is actually around 1:15 in the afternoon here because of standard time and daylight time. And then I come across here. You'll notice that the meter here changes as I come across as my solar energy is highest at noon. Okay? Now, but let's look at this at different times of the year. This exhibit is not on display at the museum yet because this is a demonstration version of it. We're going to modify it so it can be. I'm going to set this all the way up to summer. Notice that if this is east, the sun rises north of east a considerable amount. Notice too that when it gets up here, it's at 71 degrees above the horizon here in Ann Arbor. And it comes across and it sets very far to the north of west. Take a look around you. Look at the roads that are around you and watch how the sunlight changes over the year. That's the basic important thing that we have in science. The ability to look and observe and be curious to try to find out why things are the way they are. Well, let's look at the final aspects of this, which is down at, let's go all the way back down to winter. Now this is on December 21st. Notice here that as I bring this thing over slowly, the sun is very low on the horizon, way down here. So the day is much, much shorter. The further north you go, the more pronounced this is. Or the further south you go on the southern hemisphere, the more pronounced this is. So that in a place like northern Alaska above the Arctic Circle, in the summertime, the sun never sets. It's called the midnight sun. And in the wintertime, the sun never rises. It's that far north. So that's one of the wonders of the world we're in. Now, there are some practical advantages for understanding this, and I'm going to show this to you. And that is right now, I'm going to put this up to summer, and you have a house, and it's a hot day, and you really don't want the sun to shine in the windows of your house. So you put a roof over it with a long projection that faces out over the south-facing windows, so the sun can't come in, okay? There's a little bit of ambient light in here, which is why the meter is reading things. Now, however, if I move this down to winter, when you want the sun shining in, it goes in under the overhang. So if this is how passive solar houses work. They take advantage of the solar energy when it's right, and they take advantage of the shade in the summer when you don't want it so hot. So that's a little bit about that. I'm going to stop now because there's lots of other things you guys are going to want to be doing. Just remember that careers in science and technology are very, very important to the future of the world. And they're very, very important to making the world a very better place. We have lots of problems we need to solve, and they can be solved by people who have an understanding of science and mathematics. And so it's really important to do that. But at the same time, it's really important also to remember that you can have a lot of fun with science and mathematics, and you can do some interesting experiments that show the world around you in a much better light.